everyone, I'm Katie from Hackster. Welcome to the Unleash Invisible Intelligence webinar with Maxim Integrated. Today, our speakers Ben Smith and Greg Steert will be sharing their technical expertise on the Max32-620 Feather Rapid Development Platform, which is the hardware required for Hackster's Maxim Integrated contest that's happening right now. So if you already know about the contest and that's what brought you to the webinar, that's fantastic. We're really excited to see your projects. However, if this is the first time you're hearing about the contest and you're interested in finding out more, we'll be posting the link to the contest in the chat section. So make sure you take a look when you get the chance. The deadline for project submissions is August 2nd, 2018. The first 40 minutes of our webinar will be a presentation where you will get an introduction to low-powered microcontrollers, review the capabilities and schematics of the Max32-620 Feather board, learn how to extract the most power from this platform, and explore expansion options for your board. The last 20 minutes we'll have for questions. So if you have any questions during the presentation, you'll find a Q&A section on the webinar, and you can ask anything in that section on your screen. Ben and Greg will answer as many questions as possible before the end of the webinar. So at this point, I will hand over the mic to Ben and Greg, and let's get started.
Very good. Thanks, Katie. And I'm going to share my screen. And so, once again, thanks for attending our in-depth review of the 620 Featherboard. I'm Ben Smith. I'm an applications engineer. I'm based in Dallas. And today I'm joined by Greg Steert, another applications engineer out of our Oregon office. And today we're going to look really closely at the 620 microcontroller, the Max32-620 Featherboard, and cover some application possibilities. So shrink this so I can, yeah, good, I can see my notes now. So here's what we're going to cover. Over there. Perfect. First, I'm going to give you something of an in-depth look at the 620 itself. The 620 is a pretty cool microcontroller with a lot of interesting internal features, and I'm just going to give you the bird's eye view of that. Show you how it fits into Maxim's overall microcontroller strategy, and then we'll take a look at your options for development systems, and then drill right down into the prototyping platform. The 620 Featherboard is a strong prototyping platform. We're going to take a look at the power aspects of the board because the prototyping platforms really do let you get a good start on low power projects. Greg's going to cover the PMIC we've chosen for the Featherboard and how to use the Featherboard with a rechargeable battery. We'll also take a look at the expansion options that are available with the platform, and then we're going to cover some of the sensors and wireless options, and finally we'll spend the last 20 minutes in a Q&A. So be sure to write down any questions or bump them into the Q&A section, and we'll be sure and cover them at the end. Okay, so let's get started. First of all, how does this fit into the whole our whole microcontroller portfolio? Well, the 620 was introduced a couple of years ago, and it really kind of became the foundation of a whole class of microcontrollers that we're now referring to as the Darwin Class. The 620 comes in two variants. You can order the standard part, but we also have a second part that has additional security features. We call that the Max32-621. The 620 is a nice middle ground microcontroller. It has a fast Cortex M4 with floating point, DSP extensions, and low active and standby power. Now, in the world of microcontrollers, one size definitely does not fit all. So for some applications, the 620 is either too much or too little micro, and that's why we introduced the 630 that has twice the SRAM and a lot more peripheral and pin support, and the 625 with less flash and fewer pins is a smaller part. But we found that even with that, even with this family, there was still room at the top and room at the bottom. And so this year we've introduced two new families, the Max32-660 at the bottom end, still a Cortex M4, but it has a reduced pin count and a reduced feature set compared to the 625. Now, what makes the 660 special is its size. It's just 1.6 millimeters on the side in the wafer level package. and it's under $1 in reasonable quantities. The 650 takes the high end. It has more flash, more SRAM, SPI execute in place, a color LCD controller, and Hyperbus, Accellibus features. It also has encrypted external code for to keep your stuff secure. So anyway, it's a pretty cool high-end part. So the bottom line is that we cover really everything from the very highest end to the lowest end. Pretty much cover all the macros you'd want. Let's take a look at the micro we're talking about today, the 620. We'll start with the core. It's an ARM Cortex M4 with a floating point unit with single instruction, multiple data instruction set extensions. That helps you speed up digital signal processing. Now, along with the core, you're going to get all the usual suspects. You get 2 megabytes of flash, a quarter megabyte of SRAM, standard vectored interrupt controller, 6 timers, RTC, power management, the whole thing. Let's stop for a moment and talk about power management. The MAX 32620 contains a set of supply voltage monitors that are in the always-on power domain. And that means, pardon me, that means they're always monitoring the power rails. And if any power rail fails or falls out of spec, the power manager can initiate an orderly shutdown of the system. The power management system also lets you operate the device in full power mode or in any one of 3 low power modes, and the lowest of which actually removes power from the core, but it keeps the always-on domain and the real-time clock. So you can wake up very, very quickly. Yeah, usually about a 5 microsecond wake-up time up to full power. Another thing, this device doesn't need a crystal. The main 96 megahertz oscillator is completely internal, but it's disciplined by the RTC crystal if you use one. And one more thing that's not on the diagram here, there's a separate execution unit. It's almost like having a separate core. We call it the peripheral management unit, and it works kind of like a cross between a coprocessor and a DMA controller. If you need to do simple processing, but primarily data movement, you can turn on the PMU, turn off the ARM core, and you're going to operate in a much lower power, but you get a lot of the features of having a core active. Okay, so back to the slide. We're going to give you a rich set of peripherals, SPI with execute in place, I2C ports, UARTs, lots and lots of GPIO. You get a USB full speed device, that's the 12 megahertz version. You get a one-wire master, and if you're unfamiliar with one-wire, the one-wire master lets you connect to multiple sensors and use just one wire and ground. And the master can automatically enumerate and make a catalog of all the devices attached to the bus. You get analog, 4 8 kilosample per second inputs with 10 bits of resolution. You get an internal voltage reference and an internal temp sensor. And in the secure version, you get AES 128, 192, 256 for symmetric encryption. You get a modular arithmetic accelerator. So if you're doing ECDSA or you're doing like Diffie-Hellman key agreement, we've got you covered here. True random numbers, a unique factory ID. So you get some pretty cool stuff in the trust protection unit if you go for the 621 part. Okay, so that's what's inside. Let's look at the outside. You can get this in 2 packages. One is for production use, we have a 4 by 4 millimeter WLP package. It's a 0.4 millimeter bump pitch. And if space is not an issue, then we have a 100-pin TQFP. Even though the WLP looks like it has fewer connections, you don't lose any connectivity, really. You lose some ground pins and a bunch of no connects, basically. But you lose no functionality in the WLP. Let's talk about development tools. We really give you a wide range of development tools, ranging from zero-cost solutions like Eclipse and the GNU toolchain, Arduino, Embed. We also have fully supported paid options from IAR, Rally Crossworks, and the Kyle compiler. Now, for our purposes, we're really going to highlight just 3 of the free options, Embed, Arduino, and Eclipse. Let's start off with Embed. Embed may be the easiest to use. It's certainly the easiest to conceptualize. Part of the ease of use is due to its ease of installation. which is to say there is none. Everything you do is online with Embed. You edit your code in a browser, and you compile your code in the cloud. Embed is about as truly cross-platform as an embedded system can be. Standard Embed objects get instantiated on any device from any manufacturer, and that's because every peripheral is virtualized. You instantiate, for example, UART on a Maxim microcontroller exactly the same way you would on any other micro. What's the downside? Well, when you're using online tools, there's no direct debug, no breakpoints, no single stepping. You can always export an Embed application to another IDE to debug it. Now, if you do this, you're still using the Embed APIs, but you're no longer using the online toolchain. The Arduino development environment is rather similar to Embed. It's a little different, though. You don't develop actual programs or applications. You create sketches. When you're developing a program, you don't start with main. Instead, you write a setup function and a loop function. Now, if you programmed a lot of embedded, that actually makes a lot of sense. It reflects reality. I mean, that's what you generally do. You run some setup code, and then you enter an infinite loop, and that's where the actual work for the application is done. Now, unlike Embed, you don't really virtualize the peripherals in the same way. So Arduino applications are not quite as universal. But there's also less overhead. Like Embed, when you're using their online tools, there's no direct debug in the default environment. Now, the Eclipse environment is different. Eclipse is completely local. It lives on your PC and it lives on your Mac, and it offers the most flexibility, really, of the three systems we're just talking about today. You choose how you want to develop. You can use traditional C functions, or you can build your own programs using C++ objects. The thing about Eclipse is it's tremendously flexible, but it really makes no attempt to be cross-platform. The better way to think of Eclipse is as kind of a platform for platforms. Maxim has a customized development environment in Eclipse, and you can use it to build applications for any of our microcontrollers or any of our supported evaluation or prototyping systems. You can also support your own boards. The Eclipse package you download from our website is really two things. It's the Eclipse environment written in Java, originally used to develop Java program. We include the CDT, the C Development Tooling Platform. Now, the basic Eclipse environment doesn't include any toolchain. So we also provide the GCC toolchain and all of the support tools that you need to create programs for Maxim microcontrollers. One more thing, we don't use the native Eclipse build environment. Instead, we use Unix-style makefiles. And the reason we do that is all of our developers here prefer command line makefiles. In Eclipse, you get a full debugging support, and that includes breakpoints and register inspection, register modification. You can dump memory and inspect memory and modify memory, single stepping and either C statements or complete machine instructions. So if you're looking for flexibility, Eclipse is your tool of choice. If you're looking for a quick prototyping environment, Embed and Arduino really have that ground covered. Okay. Let's talk about the Featherboard. This is top view of the board, and I want to just bring to mind some of the elements that you have to work with. Over on the left is a USB port. This is 12 megabit USB, so-called full speed 2.0. For the most part, this port's available to your application. Our EV kit supports the USB for several different kinds of endpoints. So if you want to play with Embed, then or play with endpoints on the USB, we kind of have you covered there. I say in the most part because by default we include a USB bootloader that uses this port to load your application. Now you can build your own application to use the bootloader, or you just mass erase the flash and the use the SWD connector with a debug adapter to do flash programming. One more note about USB before we go on. It is a device, it's not a host. That means you could do something like, you can use the Featherboard to emulate a keyboard, for example. but you can't plug a keyboard into this port. So for better or worse, that's the nature of the port. Okay, let's talk about the SWD connectors over here. If you're not using the embedded bootloader, then this is the primary way that you'll program your board. You'll plug a debugger right there. We include a connection to the console UART via this connector also. So in one cable, you have the loader, debugger, console, the whole thing. On the right side, there's a pair of dual row headers. You can use these as connection points to connect to PMOD compatible expansion boards, and Greg's going to go into a lot more detail on that. Then up on the top, there's a battery connector. Generally, you plug in a lithium poly battery, and the PMIC will take care of safely charging and discharging the battery. Okay, also on the board, we have 3 push buttons. Over on the left is a reset button. Push that button, the processor gets reset. Doesn't reset the PMIC, so you're going to maintain your power profile and all that good stuff. Whatever power's in force before you push the button stays in force. On the right, you have a power button. Now, that power button goes directly to the power on input of the PMIC. It commands the PMIC to turn on power to the microcontroller. Now, that button doesn't turn off power. You can have the microcontroller command the PMIC to turn off power if you want to do that. This is just a way of kickstarting the PMIC and getting it running. And below the power button, there's a button marked boot, but it's really connected to a GPIO pin. So you can use that button for just a general purpose input button if you like. Next, we have 2 indicators. Both of the indicators are 3-color LEDs. They're rather different in capabilities. On the right there's a LED marked D1. It's connected to GPIO pins, 1 for red, 1 for blue, 1 for green. And that means you can directly create 7 colors. Now, don't get too excited, but 7 is the number. You can do pulse width modulation if you want to create other colors, but with direct control, it's going to be 7. But over on the left-hand side of the board, there's a LED that's connected to the PMIC. The PMIC has current drivers specifically to drive an LED. And that means 2 things, really. First of all, it's not connected to just GPIO pins. So you can't just specifically go to that LED and directly turn on a light. You have to ask the PMIC nicely. But the cool thing is that the PMIC itself can modulate the current through the LED. So you have brightness control, and you can change the color to pretty much anything you want. Okay, so that is the 620 Featherboard. There are a lot of other cool things, but enough theory. I'm going to pass it over to Greg, and he's going to give you the high level stuff. And let's see if we can figure out how to make this happen. It's over there on that screen. Yes, Greg, I approve.
Oh, thanks, Ben. Yeah, so I'll try to go into a little bit more detail on some of the features that have been highlighted and some of the capabilities of this board. Here we go. All right, so the first thing is battery management. So this the Max 32620 was designed for ultra low power wearable type applications. And so on this board, we paired it up with a power management solution that's also compatible and suitable for wearable type applications. And that has some nice advantages, but a few limitations that we'll try to go into in a little bit more detail here. One of the things we've included is the Max 17055 model gauge M5EZ. This is a really state-of-the-art fuel gauge. One of the things Maxim's been able to do is a lot of fuel gauges required you to characterize your batteries so that the fuel gauge could understand and predict the state of charge. But with our latest fuel gauge, the part actually characterizes the battery as it goes and learns the capabilities of the battery. So it doesn't need any preliminary characterization. It determines it while it goes. It does include a Coulomb counter, but it also uses open cell voltage so it can eliminate the drift in the Coulomb counter as it goes along. And all of this is done with only 7 microamps of operating current. It includes things like current, temperature, and age compensation. Also, for the battery, you need to be able to charge it and convert the voltages. And we do that with the Max 77650 Simo Buck Boost PMIC. So this is a fully featured wearable PMIC. It's got a smart power selector, which means that even if the battery's dead, it will bypass that and provide power to the system so you can boot up before the battery started charging. It does include the lithium-ion, lithium polymer linear battery charger. There is a 3-output single inductor buck boost regulator. So this is some Maxim's latest single inductor multiple output switching regulator technology. So we use one inductor, but we're able to generate 3.3 volts, 1.8 volts, and 1.2 volts for the microcontroller. And they're all done with the DC to DC, so it's very efficient. So we make the most of your battery life. And this pairs up very nicely with the Max 32620. In addition to that, as Ben touched on earlier, there is a 3-channel programmable current sync LED driver, as well as a 150 milliamp linear regulator. We're not making use of that now, but there is a output capacitor, so you could tap off of that if you choose. A couple things he mentioned, the charge LED, we label it charge because it may be useful for indicating the charge state, and it is driven by the PMIC, but you have full I2C control over that, so you can set it to use it as any indicator you want. The power button does turn the part on, but after the part's on, the PMIC has the ability, will monitor that, and it can interrupt the microcontroller to tell it that there's a button press. So you can use a power button for user input as well. One other thing I'd like to note before I move on to the next slide, both the fuel gauge and the PMIC are accessed through I2C. And there are 2 pins on the feather header that actually go to those. The P5.7 and P5.6 are the I2C bus that is used to communicate with those. So you can actually monitor that bus through those pins and see what's going on. The one limitation is that those devices use 1.8 volt pull-ups on that. So those will be 1.8 volt signals. One of the features that the Max 32620 has that's kind of unique is there are 2 I/O rails. So we actually allow you, any pin on the device can be programmed to interface at 1.8 volts or 3.3 volts. And that's just set through a register setting, which means that you can, if you can find a 1.8 volt peripheral, you'll save a lot of power because we're doing a DC to DC regulator to generate that. Moving on a little bit more about the power management and the power supplies. I mentioned that we do have 3.3 volts and 1.8 volts available. And here I'll go into kind of some of the power capabilities. The charger in the Max 77650 is limited to 300 milliamps of charge current. So from a practical standpoint, that means you probably want to use a battery about 600 milliamp hour or less. You can adjust it below that, but 300 milliamp hour or 300 milliamps charge current will take about 2 hours to charge a 600 milliamp hour battery. So you can use a bigger battery, but the charge times may not be what you would hope for. And you can turn it down lower, so you can use very small batteries as well. In addition to the battery voltage, the V-bus voltage is also available at one of the feather pins. And this is a typical 5 volt input. It's directly connected to the USB connector, so you can get whatever power is available from your USB port. If you're plugged into a computer, usually you can get about 500 milliamps out of that. But if you're plugged into a wall adapter, you can probably get an amp from that, but it is going to be dependent on your source. The system node is the output of the smart power selector. So when you're plugged into the wall, you'll get about 4.8 volts from the USB input, and that will automatically switch over to the battery voltage when you disconnect if you have a battery present. So the voltage on that pin will vary. It'll be 4.8 volts roughly when you're running from USB, but the battery voltage when you're not. There is an input limit from the USB to the sys node that will limit you to about 470 milliamps. Now that 470 milliamps will also get shared across the internal SIMO buck boost. So you can expect to get about 400 milliamps from that sys pin, whether you're running from USB or the battery. There's a couple of things you can do. You can get a little bit more current if you have a battery present to have it kind of provide for the surges. But if you're only running from USB, you probably get about 400 milliamps. The 3.3 volt regulator is one of the outputs from the SIMO. It's available in several places at the PMOD headers as well as the feather connector. You can get about 100 milliamps on that, as well as the 1.8 volts that's available at the feather connector. Remember, this is a single inductor multiple output regulator. So all of the outputs share the same inductor for generating them. Now, this is great for wearable applications, and because it's a switching regulator, you get good efficiency on all these, but it does mean that the outputs will be a little bit interdependent. So I say 100 milliamps here. We actually have a spreadsheet that'll tell you what the exact current is, but it's going to depend on the loading of each of the outputs together. So if you want, you can probably stretch this and get more current than this out of the board. But if you want to do that, you need to go look at the data sheets and use our tools like our current calculator to figure out what the real capabilities are. And moving on to the next one. If I can get this. Doesn't want to advance. Hey, Ben, is the, looks like.
Yeah, something dropped off.
Dropped off, sorry.
All right, I'm gonna go ahead and share desktop 2 again.
Okay.
All right, I'm sharing the screen.
All right, let me see if I get. All right.
And I will approve. All right, I think you're back online.
Great. So, and here we go, the next slide. So also wanted to touch on the user interfaces, a little bit more detail. Again, Ben talked about all the buttons. We've got a couple, the board comes with a little cheat sheet card that tells you which ports are assigned to these different peripherals. The reset button is dedicated, but the boot button goes to port 2.7. So when you're running your code, you can use that just as a general input. The reason we call it boot is because when we ship the board from the factory, we preload a bootloader, and the bootloader looks at the state of that pin to determine whether you want to stay in the bootloader or jump to your application code. So that is the button that activates that. But after your code's running, you can just use it as a general input. As Ben mentioned, you can use PWM outputs to create a variety of colors on the 1 RGB LED, and the power button and charge LEDs are connected through the PMIC, which you still have access to through I2C. And moving along to some of the expansion connectors. So we tried to make this as easy to connect as possible and to simplify prototyping and rapid prototypes. Rather than creating our own custom connectors, we decided to utilize a couple of the more popular expansion standards that are emerging. So especially with our low power focus, we wanted to have a form factor that included a battery. So we opted to follow the Adafruit Feather form factor. And our board will work with most of their feather wings. We are working with several of their libraries. I saw a question pop up about our support for that. We do intend to be compatible with most of those. And some of the libraries we've added in the defines to work with that. And if you find one that doesn't work, please, drop a line somewhere and let us know, and we'll try to add that to our list of tasks to work on. But I know like the LCD ones and almost all the I2C based ones are working, and we are working on the, we've got a couple examples we're getting ready to release for the NeoPixel support. Another nice thing about the Adafruit Feather form factor is this is breadboard compatible. These are a dual row that will plug into a solderless breadboard. So they're great for that if you install those headers. It's also stackable, so you can put boards below it and above it. And Adafruit has doublers and triplers and a bunch of accessories that are available. I2C, SPI, UART, GPIO, and Analog are all available on this header. And we even make our the old Dallas Maxim one-wire interface available through this header. One other thing to point out while I'm here on the analog inputs, we've got a 4-channel ADC. Those 4 channels, the full-scale range is about 1.2 volts typical, but the first 2, analog 0 and 1, we have a programmable divider that allows actually measuring 5 volts directly on those pins. And when you want to use the divider rather than setting a configuration register, because the Arduino and Embed libraries don't support that, we just call them a different input. So you refer to it as analog input 4 or 5 if you want to use the 5-volt support. And that's there. And again, here I've got a link. If you're looking for feather wings to go with this, just go to the Adafruit website, and their feathers, they have a category for wings. We also chose to support another common peripheral expansion form factor, the Digilant PMOD. So we also wanted to keep this small so that it wouldn't get in the way of other things. So we use these low profile pass-through sockets, and that gives us a couple things. One, they're low profile, but the second thing, because they're pass-through, you can access them from the top side of the board or the bottom side of the board. And you'll notice our cheat sheet card shows the pinout from both sides of the board, because one of the things this lets you do is swap the top and bottom rows of the connectors. And that's kind of important, because if you look at, for example, the PMOD type 2 and type 3, one row, there's a single row and a dual row, but the dual row, the second row is basically GPIO. Well, if you access the port 0 from the top side of the board, it matches the UART pinout. But if you access it from the bottom side of the board, it matches the SPI pinout type 2. So that's a clever little thing. We also have I2C signals available on that as well. And again, Digilant has a selection of PMODs you can choose from. And there's also Maxim. If you go through, follow this link to our parametric search, you can find a variety of PMODs that we offer as well. And again, because we're using standards, in addition to connectors, there's a variety of accessories you can get. One of the reasons we don't include the feather headers is because you may want to install a different header. You may just want a straight pin header for going into a breadboard, or you may want stacking headers or low profile. And Adafruit even has screw terminals that you can solder directly into those. It ends up being a lot easier to solder in a new connector than it is to remove one we soldered in for you. So we just choose to leave those empty and let you install whatever you want there. The PMOD sockets, we do provide the connectors there that are accessible from either side. And if you'd rather connect a cable or change the gender on those, Digilant has a lot of accessories you can choose from. So, and one other example, I mentioned cabling. If you had like a right angle single row connector, you could plug a pin header cable into that, use it for fly leads. One thing I created that helps with that, so that cable, oops.
Wow. That's
yeah.
That's not a happy thing. Just a second.
Sorry. But I created a little clip that helps secure the cable to the board. And there's a link. You can just purchase it directly from Shapeways, if you'd like to get something like that. And I'll try to make the 3D model available as well.
And let's go to, sorry. You're pretty close to the end here.
Yeah, we just got a couple slides left. So
all right, there you go.
Almost into the.
Are you still driving?
Yeah, I think so. Here we go. And another thing with these fairly standard connections, you'll notice we didn't put a radio on board, and that's because there's a lot of different radio standards. So with all the connection options we've provided, there's a lot of off-the-shelf ways you can add a radio. This is just a few that we pointed at. If you're looking for 2.4 gigahertz like Wi-Fi, Bluetooth, or BLE, Digilent offers an ESP32 module that would be compatible with one of the PMOD sockets. If you use a right angle connector and a cable, you may even be able to connect that and still have access to the feather connectors. There's also, if you're looking for the sub gigahertz, you need a little bit longer range, lower power. Adafruit has a couple feather wings for either just a generic ISM 900 megahertz interface or LoRa. And I can provide an example to a couple Arduino and Embed examples that use this, that support this radio. And if you're looking for another wired interface, there's both Featherwing and PMOD interfaces for that, as well as a variety of other ones if you go through those sites. Again, we're just trying to make it as open as possible. And a lot of these links we're providing and a lot of the details, I've created kind of a cheat sheet for the board on Hackster.
Again?
Try to wonder if I can
hang on, let me drive for a second.
Yeah.
There's the mouse.
So I've got a cheat sheet, and we're going to send out the link for this. It'll be in the video and post it in the discussion on the site. So you'll have all the links we're talking about and much of these details. And again, a lot of this information will be available in the Hackster project cheat sheet as well. And again, we're just a couple more slides here, and then we'll get to the Q&A. The cheat sheet. Another thing, like, so where do we go from here? So after you've got your proof of concept made, you know, we want to make this as easy as possible for you to take this to the next level. So we fully, to make it as easy as possible for you to develop your own board, we designed this board in Autodesk Eagle, and the CAD files are available on GitHub. The link's here. It's on the cheat sheet page. We can provide that. Autodesk Eagle, it's the same tool that groups like a lot of stuff in the open source hardware and Adafruit use. So it's fairly inexpensive, and there are some free options, but go ahead and use that. There's a lot of, and even more coming with to build these boards for you. Things like OshParks, Seed Studio Fusion, Macrofab, a lot of opportunities who will help you make these inexpensively. And then again, promote. There's places you can actually try to monetize. We'll help you monetize that. Crowd Supply, Tindy, Indiegogo, Kickstarter, things like that. And definitely share your projects on Hackster.io as well. But we're trying to make this as easy as possible, so we're providing you access to the CAD source data. And at that point, I think we're done and we're open for questions.
Great. All right, so we have a few right now, and if anybody has any other questions, feel free to ask them in the Q&A section, and we'll get to those. Also, I will send right after this during, well, Ben and Greg are answering your questions. I will also send a link to the discussion page on our contest page, so you can send any questions you have later to that, and Greg and Ben are checking that and answering some technical questions there. Or you can send any questions to help@hackster.io as well, and we'll get it to the right people. So with that, the first question that we had was, can I use, and I think Greg maybe touched on this slightly, but can I use my existing Featherwings board with this, like my Add-A-Logger? Is it fully integrated with Adafruit Featherwing library?
And I actually, the Add-A-Logger specifically, I have tested their example code, and that should run on this board without modification. You'll have to specify maybe a different pin number if you're using that, but otherwise, yeah, we work with that library. And if you find a library that doesn't work with our board, please try to reach out to us or send something. Our TTS group monitors a lot of this stuff. So if you actually go to the Maxim website and submit a service request, that should get routed to the right people.
Great. All right, and the next question is, could you provide a 3D file of the Featherboard, such as a STEP, S-T-E-P, so I can include on my custom 3D design? Excuse me.
So I haven't worked with the Eagle 3D export, but I believe it's they included that. So you could do that. Because we provide the Eagle CAD, you could use their export, or KiCad, KiCad, depending on how you say that, will import Eagle files, and I know they have a pretty extensive 3D modeling support. So just grab our CAD files and import it into Eagle or KiCad to export the 3D model.
Great. The next question is, can you provide, excuse me, sorry. Can you provide the mate PN of the battery connector?
Yeah, if you go to our GitHub page with the CAD file, and actually I think the part number for the connector is in the data sheet for the Featherboard as well. So that'll give you the part number, and then you can go look up the mate. It's the same one that Autofruit uses on their Featherboards. So most of their batteries you can buy with the connector. They're one of the better sources. I buy batteries from them, and SparkFun uses the same the connectors as well.
Great, sorry about that. All right, the next one we have is tutorial to use Eclipse with the Max 32620. Is it compatible with Embed's API and libraries?
Embed, the Eclipse BSP that we provide, and actually I should say the GCC BSP that we provide isn't directly compatible, but there's when you export an Embed project, one of the options is that you can export it for GCC, and that will compile. It's not going to use any of our BSP libraries, but it will use our Embed our Embed objects, the Embed functions that we interface functions that we create. So yeah, you can get it into Eclipse and get it to compile there. You're not going to be using our direct BSP functions.
Right, and another thing to add, Embed also has an offline command line version. And if you install our Eclipse toolset, that will install all the GCC compilers needed to work with the Embed CLI. Because when you install the Embed CLI, that gives you the access to import and export Embed projects. But you still need to point it to an ARM tool chain, and installing our Eclipse tools will give you an ARM tool chain that's compatible with our microcontrollers. So you can use those together as well.
Great. All right. Part of the same question, it says, how do you access RTC for timekeeping?
Yeah, so actually, it depends on the platform you're using, the IDE you're using. Embed has an RTC API, so you can use that. That should be working with this board. I've checked with that. We support that. Otherwise, if you're using our Eclipse tools, we have an RTC example you can look at. And if you're using Arduino, you can also go look at the examples we provide with our Eclipse tools and implement those inside the Arduino code. One of the things some people don't realize is that when you install our Arduino board support package, we include our standard Synthesis libraries, so you can actually include and call some of the functions from libraries like our RTC library.
Yeah, and one more thing, the RTC is a critical piece of this thing, because the RTC lives in our always-on domain. So the power domain is is always going to be available. That means you can shut down the processor, run it in like low power mode 0 or low power mode 1. The core itself is now turned off. You're drawing literally microwatts of power at this point. but the RTC can wake you and then get you going again. Those wake from sleep examples are already there in the Eclipse package that you get, and I encourage you to have a look at those.
Great, thank you. All right, Eclipse for Embed example code for accessing internal PMIC and fuel gauge. Do you have that?
If you go to the Embed project page for the board, we do have a couple basic examples that show accessing the PMIC and fuel gauge. We are working on more examples. I don't know that we have many examples for this board in Eclipse yet, but we're working on adding that. And as we get those, I'll try to put those on that cheat sheet page to give more links for these types of examples. But if you're using Embed, a great starting point is the Embed platform page, because we usually post our examples there.
Great, thank you. Okay, next question. How to reset Max Pico to be programmable as standalone board again?
Okay, so are you talking about resetting the Pico board so you can run your custom code in it, or resetting it so that you can return it to DAP-Link capability? I guess I need to.
I think the former. I think they want to. It's a DAP-Link board, and I think they want to run their own code on it.
Well, and actually, I can touch on this, and I think it may answer both. The bootloader that we use on the Feather board that we ship with is actually very similar to the bootloader that ARM uses on their DAP-Link controllers, which is the same one we're using on our Pico board, which was designed originally as a DAP-Link controller. So essentially, this bootloader is a set of code that runs when the part initially powers on. And it's used for updating firmware. So, but it needs to know if you want to do a firmware update or if you want to run your code. So the way these boards determine that, make that determination, is they monitor the button. On the Pico board, there is only one button. So if you hold that button while you're applying power, that will tell the board that you want to do a firmware update. And that doesn't matter if you want to replace the DAP-Link or update the DAP-Link code, or if you want to install your own code. There actually is a platform page for the Pico board, and you can actually program those in Embed and create a binary file that you can drag and drop into it to replace the DAP-Link image. But then if you want to return it and make it a DAP-Link again, you hold the button down while you're applying power and drag and drop the file. All this Embed stuff is drag and drop. So it's a USB mass storage device for updates. And actually there's a page linked, I think it's linked on the Pico page. I need to check the links, that will have the default DAP-Link image if you want to return it to a DAP-Link. One other trick I noticed that on the Pico board is very small, and sometimes it's difficult to hold the button while you're connecting the micro USB cable. So my suggestion is plug in the micro USB connector first, hold the button down while you're plugging in the other end of the cable, because it's a lot easier to do that dance that way. So if I didn't cover what you're looking for, please ask another question.
All right. One person had a question. They wanted to know why there was no I2S peripheral on those M4 CMU.
I think the main thing for that is that these were really targeted at wearables, and that at the time we created these wasn't a common wearable feature, but it is something we're seeing becoming more popular, and we're planning that in future products.
Yeah, stay tuned.
Yeah.
Great. All right. Can I use level shifter to work with 5-volt sensors, or just stick with 3-volt components?
All the I/O on this part are 3.3 volt capable. We don't have any digital 5-volt signals on this part. There are the 2 analog inputs that can accept 5 volts. So if your joystick had an analog input, it's only a 10-bit ADC, but if you're using an analog joystick interface, you could use those 2 pins. But otherwise, I suggest sticking with 3.3 volts, or if you really are in battery optimized, even try to use 1.8 volt where possible.
Great, thank you. Okay, next question. We got a lot of them, so this is great. Thank you guys for sending all these questions. All right, I want to include for my project 9-volt LEDs at 20 milliamp. Do you think there's any problem if I connect an additional booster regulator to the 3.7 volt battery? I wonder if this could interfere with the already included regulators of the board or the battery charger.
So if you're doing this, my suggestion would be to use the feather expansion connectors and use the sys pin, because that sys pin should have no problem providing that. And it basically provides the same voltage available on a lithium ion battery. And there's a lot of LED boost regulators designed to run from a lithium ion battery. So it'll look basically the same. The one difference you get there is that the PMIC will take care of controlling the current, so you can boot from dead batteries. You'll also be able to run from the USB power. It'll automatically do that switch over. So my suggestion for adding a 9-volt boost regulator is to draw the power from the sys pin, and you shouldn't have any problem.
Okay, is the Arduino IDE RTC API documented anywhere? Are there examples?
I don't know if we have examples for the RTC in Arduino. I know there's an API in Embed. I'll have to look into that and see, and we can add that to the list of examples to add. I think that would be a popular one for our Arduino PSP.
Great. All right. How do you specify in a program when you are using a pin for GPIO or for the assigned function like SPI or I2C?
So that's going to be different depending on the IDE you're using. With Embed, you basically instantiate one of their APIs and you tell it which pins you want to use. Arduino uses a pin numbering scheme, and some of the functions are predefined, so it's a little different there. And in Eclipse, you would use our GPIO libraries, and we have a routine that specifies what function is at that pin or how to select the alternate functions. So it depends on each one. So you would have to go to that IDE and look at some examples.
And let me give a little color to that, because we actually do have a pin mapping tool. That's an online tool. So you can go in and say, okay, I want to use UART0, UART1, SPI0, SPI2, and an I2C port, and I don't care which one that is. And I want to set all that up, and it will show you your various mapping options available for that. And then that tool will also generate some code that's compatible with the Eclipse environment that you could pull in and set all that stuff up. So the pin mapping can be pretty flexible, but it's pretty cool to have the tool go ahead and generate all that startup code for you, so you don't have to struggle through, well, this register needs this and that register needs that. If you're in, like Greg said, if you're in an embed, it all handles that for you, and you don't have to sweat any of those details.
Fantastic. I think that looks like everything that we have for questions. Is there anything else? If anybody has any other ones, they can write them real quick and send them in, and we can get them answered. Otherwise, thank you everyone for checking out our webinar. And like I said, I posted some things in the chat section, so there are some links, and I will share this link that Greg made for his project right now, so go ahead and grab that. But we're really happy that you came. If you don't know about the contest, make sure you go check that out. Like I said, that is also in the chat, that link, and we will also add these to the contest page. So these links will be on the contest page, as well as the recording of this webinar later this afternoon. Hopefully, we'll have that up on the contest page as well. So if you missed something or came in late, you can go check that out.
And one other thing, if you think of a question afterwards, we're monitoring the discussion boards for the contest, so that's a great place to post these questions as well. Yes,
thank you, Greg. And I also added that link as well in the chat earlier. So if you wanted to go directly to this discussion page, that's in there as well. But you can get there from the contest page itself. So, any other last thoughts, Ben or Greg?
No, we just want to thank everybody for showing up and attending. And yeah, I'll echo Greg's sentiment. If anything comes up, if you have any questions, we will be monitoring the rooms. Please bring your questions, and we'll answer them as best we can.
Great. Thank you so much, Ben and Greg. We really appreciate you coming and sharing your expertise with us and answering those questions later if people have them. So I hope you all enjoyed our webinar today, and thank you so much for joining us. Bye.
Bye-bye.